We are working as usual, but looking for a fast and reliable solution to store our data. My boss was sitting on a couch, on a couch, helping us to validate a proper solution. Suddenly, something passes by very fast, like lightning. Whoa! What was that? Asked my boss. Maybe a manga monkey, an electrical current from a dynamo? He questioned. Or a hornet bus, or a rabbit, a raptor? Nope, I replied. It's something really fast that can see beyond what our eyes can see. Unbelievable, he yelled excitedly. Yes, boss, I said. It's Apache Cassandra. So, good morning, everyone. My name is Eiti Kimura from Movile, Brazil. And I'm going to show you a little bit about our use case and how we use Cassandra in Movile to bump up our startup business, all right? So let me show a little bit what we are doing in Movile. So we're an industry leader for the development of mobile content and commerce platforms in Latin America, entertainment apps for adults and kids, many options for buying with confidence, and for companies, we deliver complete products, integrating transactions, mobile payments, and content distribution. Here are some of our products. We have the Play Kids, offer hours of age-appropriate fun and educational shows, and we have books, we have entertainment for kids. It's a award app and considered as a top kids app in Latin America, Brazil, and some countries of the world. And so we have the free zone that can scan and connect you to open Wi-Fi hotspots. So we have the iFood. You can easily ask food using your smartphone with just a click. It's pretty easy and fun. And we have Ziwi to find coolest videos on the web and see what your friends are seeing. You can share. So it's very nice. And so for companies, we have solutions for learning, for news, games, and TV. We carry our business, right? So I'm going to show a little bit about our platform. Then I'm going to present you the architecture here. So we have a subscription and billing platform. So it's a REST-based service API. It handles subscriptions and charges in carriers, and it's responsible to renew the expired subscription as well. This system must be fault tolerant, and this platform is basis for the carrier business to build service products and application. It's responsible to keep running our core business with carriers. It's a pretty critical platform. Well, some numbers. We have about 50 million subscriptions right now. And we have our API receiving about 50 requests per second, where the main operations are the subscribe, cancel, and profile. And our renew engine it does about 52 million of billion tries a day. It's about 603 requests per second through the carriers. And this is how our data are distributed. Most subscriptions are concentrated in Brazil, which is represented in green, and Mexico in purple. And on the right side, so the spots are on the countries where we have subscribers in South, Central America, and a few in North America. So now that we have an idea about the nature of data, the volume, and how we use it, let's see how simple architectures have to evolve to accommodate and process a large volume of data working in a distributed fashion. Here's a quote from Martin Fowler's book. There isn't just one way to state a system architecture. Rather, There are multiple architectures in a system, and a view of what is architectural significance is one that can change over the system's lifetime. So the systems are evolving all the time. The requirements change. Your business change. We need to be prepared to handle these changes. Well, here I have a very basic architecture. It's simple, it's common, it works for the most low traffic and low processing applications. That's the way we started in about, I think it's 2007, we have this kind of architecture. Yes, it's working. Then we have to increase the load, increase the people accessing data concurrently, and we have our renewal system attached to the relational database. This model was working, but our user database was growing and growing. But something changed, you know, our requirements changed. So we had to be scalable, high availability, and high performance. So the first step we did was just to scale and scale our application layer. And we had a cluster of service APIs connected to our relational database. Our database starts to suffer in these times. Then with very high usage, the system goes very slow, okay? Very slow system response. So overall throughput decreased, low availability, single point of failure, and even worse than stopping to only work sometimes. You can see, so in the center of the image, the database is burning. It's our bottleneck, okay? So one lessons learned here is that you have to scale your application layer, but you have to scale your database storage, your cache, your queues. You have to scale as well to follow your system and business growing. Well, we have to decide with this point to change to our database storage engine, to move from the relational model to NoSQL model using Cassandra. And now I'm going to show you our currently designed for a distributed database using Cassandra. Well, the operations are distributed across the nodes. We achieve linear scalability, the Cassandra ring in green in this image. I can add more nodes, whatever I need. I can add more systems instances, and it's going to work and going to be all right. So the performance issues were solved. The availability has improved. There's no longer a single point of failure. All of nodes can serve data and can receive read and write requests. So the load are distributed across the nodes, and the performance has increased significantly. Okay, so now you can see how Cassandra fits to our solution to make our applications be more kind of a consistent, increased availability. And now I will go show you a little bit how we did this. So how we changed our data model to achieve this kind of setup, this kind of architecture, and how we did our hardware configuration, and a little bit about our cluster. Well, data modeling. So the normalization, writes are cheap, reads are expensive, so insert data in every arrangement that you need to read. Don't be afraid of denormalization. It's not evil, I think. So there are 3 different ways to model a solution. There are different ways to model a solution. There is no right or wrong way. There is the one that best works for your nodes and requirements. So it's very important. You need to model according to your requirements, according to what you need, how you are planning to retrieve data from the database. So try to model thinking about and how you can retrieve data, how you can write to match to your performance requirements. Plan your queries and how you need to get the information before modeling. Use it as a driver for modeling decisions. So I'm showing you two versions of data models. The version 1 that we use at the beginning using Cassandra, and the version 2, an improved version that we have to move to get more performance that we need. So our version 1, so here this SQL syntax, all right? I have, so this model relates to the users and their subscriptions. It's consistent. It's consistent. It looks like a traditional relational database model. And so we have subscribers and the people that has subscriptions to our products, to our service, and so on. And that was the first representation we used. And here are the tables with some data. So it's a relationship of one-to-many. The users are identified by their an ID. It's the phone number. And each user has maybe one or more subscriptions. And these are our first model representation. So it works. It's okay. But so we mapped that the most used function of our API was the profile one, to get the user subscriptions and the status of each subscriptions. So I'm show you here to simulate how to get data to mount a profile response in our API. So it's done basically in 2 steps to do that. So the first step is to check the index table to get the IDs of subscriptions for a given user. So select star from user subscriptions, where phone number is this one. Okay, I have 3 matches in this example. And I have the returned data. So it's an index table, okay? So now the second step, I need to query all the users' subscriptions by its ID. Notice I had to do a query per record that has returned from the previous query. I have the index, I have the subscription IDs from a given user, and I have to query the subscription table to get the subscription for this user. So I have 3 queries here, but if in case this user has more subscriptions, like, I don't know, 10 or something like, I have to do a lot of queries to my table, and it's pretty expensive. It's known as client-side joins, and you have to do a lot of remote calls, and it costs, in terms of performance, it's a bad practice. So yes, we changed a bit about our data model, and in our data model version 2, now that's what we have. We have just only one table for subscriptions that relates subscriptions and its subscribers. Okay, I still have the phone number that identifies a user, the subscription ID, and here the serialized blob. It's a new design decision that we take. So we decide to serialize all of subscription objects into a blob field. We had about 50 fields attributes in our subscription, but we decide to serialize it to keep the data smaller to traffic for network traffic and so on. So in this model, so I have this is our data in our new model. So notice that now I have the serialized data. It's a array of bytes, okay, and no more the fields with the values. So to query now a profile of a user, it becomes so pretty easier. Now I can do just a select star from subscriptions where phone, it's like the phone number, I have my matches, and I have all of data that I need in my hands. I don't need to do so a lot of other requests or queries, but it's a very pretty better model than the previous one. So that's a question: why did we decide to change our storage strategy and start to serialize those fields? It's simple. It's a part of our storage strategy. So represent information, so it's complex. It depends on your purpose and how you want to use it, okay? So we tried some various ways to store information. It optimizes network traffic as well with this solution that we have adopted. So here I have the types of object representation and in the object size in bytes, the very same subscription representation in XML, Java byte array, JSON, and Google protocol buffer. So now we have, our solution is to use the Google protocol buffer. It's about 500 bytes, and it's as very small objects to go to the database. And the result to using this kind of approach, you can see right here, where we have our database size and our storage strategy, size in gigabytes, you know. So we moved from the Java byte array solution at about 93 gigabytes to protocol buffer solution that is about 20 gigabytes. Okay, data size decreases considerably, so less data to handle means more performance and less network traffic. Well, data model. So performance increases significantly, so reduced complexity from 2 tables to 1 table. It's simpler, it's lighter, so reduced number of remote calls. In our data model version 1, I had 1 query to index table and X queries to 1 per index returned. So in our version 2, we just have one query that brings all of the data, and the data volume has reduced. So that shows how important it is to how did you plan your data model based on your needs, all right? Okay. Now, so I'm gonna open up our Cassandra cluster configuration with hardware specs and so on. So it's geographically distributed. We have 2 data centers in São Paulo, Brazil. Here our ring topology. So notice in the data center 1, we have 4 nodes, and in data center 2, we have 3 nodes. We are running with vNodes configuration right here. So now we have a very good hardware infrastructure, but so I'm going to show you a version 1 of our hardware infrastructure, and then an improved one. It's called version 2. In our first experience with Cassandra, we just had 4 servers, running with one SATA disk and one SSD with Apache Cassandra version 1.06, okay? And that's our first configuration. It works very, very nice, and it was able to handle about 40 million subscriptions and subscribers with no problem. So we decided to upgrade our cluster, to scale it up and scale it out as well. So the new version of infrastructure configuration is this one. Now we have 6 servers and 6 virtual machines. We notice that now we have 2 SSD disks, and they are configured as a RAID 0 configuration. It's a very, very fast for performance, and we are now using Cassandra 1.2.13. So as you can see, we still have a server from a previous infrastructure. All right, our key space. Our key space is configured so with a replication factor of 3 per data center. Here are column families. We have subscription organized by subscribers, delivered tickets used for synchronous billing with carriers. So hard limit control and rules are used for safety mechanism to prevent overcharges. We have an index config. It's a lookup table to find subscriptions for a given configuration. So user directives used to store our blacklist and whitelist information. So I have two of those column families here. So the subscription has about 46 million keys, and hard limit control has 44 million number of keys. And so notice the read latency and read and write latency. It's way fast, you know. So our overall cluster response time, we have I just separated to the data center 1 and data center 2. So pay attention to the write and read latency per node that I have, and our total number of operations per second. It's about 13,000 reads and 9,000 writes per second. All right, some operating system and software customizations. According to the Cassandra docs, the recommended settings for production, we're using Oracle Java 1.7 plus JNA configured. We disable the swap, and we install NTP servers in all of the servers to synchronize the server's clock. Some limits configuration. We have increased the number of the open files to 100 from the default configuration to 100,000, and the allocated memory to unlimited, and addressing virtual memory as to unlimited, and number of open process to unlimited as well. Well, here we have a graph. So in orange, you can see the total reads per day. It's about 600 million, and in blue, the total writes per day. It's more than 400 million. With together, it counts more than 1 billion operations, Cassandra cluster operations per day. Some conclusions. Why Cassandra? Well, good performance for reads. It has excellent performance for writes. Read and write throughput, highly scalable. It's linear If you need to double capacity, just double number of nodes. It supports geo-distributed information. It's fault tolerant. It has tunable consistency per client, and free and open source software plus support. So thank you. Thanks for coming. Here are my contacts.